Today we are going to start chapter 9, which is going to be the last chapter we're going to cover in this semester. Um, so there are several major things I want to cover in this chapter, which is, okay, the first most important thing is the universal law of gravity. Okay, the second thing we're going to talk a little about the application of this law. Newton actually he found out not only the objects on Earth has gravity, but also this gravity is universal, which means that this gravity applies to any objects in the universe. That's why we call this universal law of gravity. Okay, so the law of universal gravitation means that everything pulls on everything else. Everybody attracts every other body with a force. That is, remember, this is attraction force, okay? That is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. So if we write down that law in the format of equation, you can see the force actually is proportional to mass 1, mass 2, and distance squared. So if you have one object over here, mass 1, the other object is mass 2, the distance between these two objects is represented by D, and then there is a force actually acting between these two objects. Okay, so the objects could be normal objects on Earth, or could be any object in the universe, could be between Sun and Earth, could be between two galaxies. Okay, so the force again here is proportional to mass m1, m2, and inversely proportional to distance squared. So in other words, if the mass 1 is bigger, the force is bigger. If mass 2 is bigger, the force is bigger. If the distance is getting bigger, actually the force actually is getting much smaller. Okay, so that's the first thing. The second thing here is that this force is an attraction force. So which means that, okay, if you have M1, M2, so M2 actually has a force on M1, which is attracting, meaning that it's pointing towards M2. If you connect between these two together, these two objects together, so the force, we say force 1, force M2 acting on M1, we say F21 is pointing along this direction. And at the same time, based on Newton's third law, M1 has a force on M2, so which is pointing towards M1. Again, F12 means mass 1 is acting a force on mass 2. So you can see these two forces actually, they are action-reaction forces from Newton's third law. So they should be same magnitude but opposite direction, but they are pointing towards each other because this is an attracting force. And gravity is the weakest of four known fundamental forces. So here I want to just emphasize, just introduce a little bit about what are the four fundamental forces. Gravitational force is one of them. The second type of fundamental forces is electromagnetic force, which happens between the charges or magnets. And we have strong nuclear and weak nuclear forces. Those forces are happening inside atoms. Okay, but the gravitational force actually is the weakest among those four fundamental forces. So, and then again, if we write down a complete equation for this universal gravitational law, it is written as F equals G times M1, M2 divided by D squared, where capital G is called universal gravitational constant, which is a very tiny number. Okay, so I want to just, talk a little bit about this equation, and then I want to give you some examples about this equation. So as you can see, this equation here, G, is a very small number. It's a very tiny number. 10 to the negative 11, 10 to the negative 11, right? So that's why, when you have not so big mass here, when we think about two people on Earth, let's say, for example, because those mass are not relatively small compared to the mass of the Earth, for instance. So when we have two small masses multiplied by this even smaller number here, this force becomes very tiny. Okay, so the force is very, very small. So that's why in most of the cases, okay, we don't talk about the forces acting between two people, okay, because this force actually is very, very small. So we don't feel it. It's very tiny. But on the other hand, in the universe, if we consider sun or earth, for instance, okay, the sun's mass is 2 times 10 to the 30 kilograms. The Earth's mass is 6 times 10 to the 24th kilograms. So we're talking about huge amount of mass here. When the masses become bigger, okay, so this g in 10 to the negative 11 actually is not a big deal. So as a result, this force becomes big enough. Okay, so that's why this law actually is used a lot in astronomy when we talk about the objects in the universe. Okay, I'm going to give you just 2 examples. First example is, remember, okay, when we talk about free fall, I just gave you this number, which is g equals 9.8 meters per second squared. But I didn't tell you why this number is 9.8 meters per second squared. So in this chapter, actually, we can verify that indeed this little g is 9.8 meters per second squared. So for instance, if you consider a person over here, so this person is mass, the mass is m, and we have Earth here, so the mass of the Earth, okay? And then because between this person and the Earth, there is a gravitational force. So we can use this equation to calculate it, right? M-E. And then we're assuming this is the center of the Earth. That's the radius of the Earth. So we can calculate the amount of force acting on this person. And also we know this force actually is the weight of the person. We can use M times G to calculate it. If you compare, if you look at these 2 equations, okay, if you look at these 2 equations, they're equal to each other. So in fact, if we single the mass out, and we can find out this little g actually equals g m-e r-e squared. Now we can find out, okay, we can plug the numbers in, so where g is 6.67 times 10 to the negative 11 times the mass of the Earth divided by the radius of the Earth. The radius of the Earth is 6.4 times 10 to the 6 meters per squared. If you do this calculation, okay, you should be able to find out this g actually is approximately 9.8 meters per second squared. So as you can see now, based on Newton's universal gravitational law, indeed we found out this g, which is we call gravitational acceleration on Earth, is 9.8 meters per second squared. And it depends on the mass of the Earth, also the radius of the Earth. So if you imagine we move the object to the moon, because moon's mass, moon's radius is going to be different, so that's why the gravitational acceleration on moon is going to be different from the gravitational acceleration on Earth. So that's the reason why we learned before that, you know, if we move the object from one planet to another planet or to different locations, the gravitational acceleration could be different. So that's the first example. I want to give it to you. The second example, you know, we can just calculate. We're going to calculate the force of gravity. Between Earth and Sun. So we can use this equation again, Earth, Sun, and the distance between Earth and Sun. So that's the equation. So we plug the numbers in. I'm going to ignore the units because I don't have enough space here. Please remember, when we talk about this law, the distance here is the distance between two objects, and then distance has to be squared. If you do the calculation, okay, I want everybody to take out your calculator and verify indeed you can get this answer. Okay. The unit, of course, would be in newtons because we're calculating a force. Okay. So again, this law talks about the force acting between any two objects in the universe. So now I want you to go back to look at the slide here. Okay. If you can pay attention to the format of this law. Okay. The format of this law actually again is F equals G m1 m2 distance squared. Okay, and we call this actually F is inversely proportional to D squared, right? And we call this kind of format, okay, if you go back here, is inverse square law. So you have to remember, you have to square the distance first and then do the inverse. So when you increase the distance, the force actually is going to be decreased. So if you look at example here, if you have a can of paint, you're trying to paint the areas actually at different distance away from the paint. And you can see that when you spray the paint, okay, it's going to be more spread out as the distance goes further away. So initially you have one area unit, okay, here, and then but it's when this area is 1 unit of distance. But when you have 2 units of distance, then it's going to be 2 squared, which is going to be, the paint is going to spread out into 4 different area units. And then the thickness of the paint becomes 1/4 of it. So similarly, when you go here, it's going to be 9 and 1/9 and 16th and 1/16th of it. So this shows you how the inverse square law works. When we apply Newton's gravitational law, okay, we can see that when we plot the gravitational force as a function of distance, when the distance actually is quite close, and then you see the gravitational force is big, but as the distance goes further away, okay, especially after 5D, you see the gravitational force becomes so small. So when we talk about gravitational forces, okay, when the distance is much, much further away, so we can kind of ignore this force because this force actually is it becomes very tiny. Okay, this topic I will talk about it next class. So on the Blackboard, I posted a worksheet, which is related to inverse square law. I'm going to ask you guys to work on that after class. Okay, and then next class we will come back to finish up this chapter.